Transition metals. Transition metal naming is different from naming just normal, ordinary inorganics. For example, NaCl. NaCl, that's just simply sodium chloride. Now, sodium is in group 1, so it's outside of the transition zone. Sodium's way over here. So you just call it sodium. Now, any element in here, you can't just simply say iron, for example. You have to say a little bit more about the iron. Now, why would that be? Well, it's because iron can have more than one charge. Iron can be +1, +3, +2, +4, +5. Iron can be a whole laundry list of charges. In fact, most of the transition metals can be a whole laundry list of charges. There's a few that I think can't be, but most of them can. For example, gold. Gold can be 2 charges, 2 stable charges. There's more than 2, but there's 2 that are stable. So that's the idea. You have to tell the user or the reader what charge you're dealing with. So for example, if I had FeCl2 or FeCl3, those are 2 very different molecules, 2 very different chemicals, okay? They're not the same. As you can see, this one has 2 chlorines and that one has 3. They're different. They're not the same. So now if you were just talking to someone, you said, yeah, we used iron chloride in this reaction. Well, they're not going to know which one you used. They're going to think, well, which one did you use? Did you use iron 2 or iron 3? So that's why we have to give it a Roman numeral, to let the people know what exactly we're doing. So to name this compound, you guys right now would have said iron chloride, and that's partially right. Partially right. How you'd actually name it is iron, parentheses, 2, parentheses, chloride. Now I know everyone's looking at that saying, oh, the 2 came from here. Not so fast. Not really. The 2 did not come from there. You used the chlorine to figure out the 2, but it didn't come from there. Here's where it comes from. You have an iron in this molecule, and you have 2 chlorines, right? So just draw them like that. Just draw them out like that for now. And then you go over to the periodic table and you say, okay, iron. What's the charge on iron? Oh, iron's in the transition zone. Iron's right here, smack dab in the middle of the transition area. So iron is right here. So iron is a transition metal. This is a transition zone. So iron must have a Roman numeral. How do I figure that out? Is it iron 2, iron 3, iron +7? What is it? It's very simple. You look at the other ions, the negative ones. The negative ions are what you look at. Look at the negative ions. Chlorine has what charge? -1, right? Everybody? -1. It's for a grand total of how much? 2. So now, the chlorines bring a -2 to the molecule. You with me on that? Everybody? We all know that this formula must have a charge of 0 when everything is said and done. Is that correct? Yes. So if the chlorines are bringing a -2, the iron must be what charge? 2. +2. And that is where the 2 comes from. This corresponds to that. Okay? The Roman numeral has nothing to do with how many anions you have. Nothing. It has to do with how many negative charges you have, because it has to equal those. Right on? Thanks. Okay? So now here, we have iron with 3 chlorines. Well, first of all, before we get into that, does everyone get that? The charge on the metal is the Roman numeral? Okay? So it's iron 2 chloride. All right, let's do another one. The one beside it has 3 chlorines, so let's just draw those chlorines out. Cl, Cl, Cl. Look at your periodic table. Iron is still in the transition zone. Pesky iron. So iron is a transition metal. It must have a Roman numeral to tell us what the charge is on the metal. Chlorine. Chlorine is what charge? -1. So -1 negative 1 for a grand total of negative charges of negative 3. So the iron must be positive 3. Right? So this one is iron, open parentheses, Roman numeral 3, close parentheses, chloride. And the top one was iron 2 chloride. Okay? That's what it means. Now this plus 3, again, the plus 3 goes with the charge on the metal. The Roman numeral tells you the charge on the metal. Go ahead.
The negative 1, you got that because it wants to be in the group 8?
It wants to get one more electron to look like a group 18 element.
Okay, so going to the right is going to be negative.
Gain electrons, yep. If you go to the right, you're gaining electrons.
So, no, that's what you're saying. Gaining, it'll be a negative.
Yes.
Electron.
Yeah, because you're gaining negative charge.
Okay.
Right up?
So going to the left would be positive.
You're losing negative charges, right? If you go to the left, you drop electrons off. So the only ones that go to the left, though, that we know about are 1 and 2.
Okay.
And the transition metals will too, but we don't know how many they'll give away.
Okay.
So all metals can become positive. Okay? Everyone, so far so good, right? That's not too hard, right? Everybody okay?
Yeah.
Always pays to do more examples. Okay, let's do some more examples here. It's not hard, it's just you got to get used to it. You got to practice it a little bit. Okay, so what if we had, let's pick a different metal. Everyone's favorite. Gold, there you go. Okay, it's a little trickier now. Let's do the top one together. So now we have Au, which is gold, and we have O. We look for gold in the old transition zone. So we see, okay, where's gold? Here it is. Well, crap, it's a transition metal. So we have to figure out what charge it is and give it a Roman numeral to tell the reader what charge the gold must be. We can't do it from the gold because it's in the transition zone, so it could be anything. So we look at the oxygen. We know oxygen must be negative 2. So there's one oxygen in this molecule, it's negative 2 for a grand total of a negative 2 charge. There's one gold atom, so what must the gold atom's charge be? Positive 2. So it's actually a gold ion, Dr. Betts. So that's called gold 2 oxide. Gold 2 oxide. Okay? Everyone see how I did that?
Yes.
Everyone comfortable with that?
Yes.
You may not have known Au was gold, but you understand the 2 though, right? This 2 goes with that number right there. This 2 has nothing to do with that. Notice how there's only one oxygen. So it's not iron 1, or sorry, gold 1, it's gold 2. Here's one. Now we have 2 golds. And a sulfur. So now, what's the charge on the gold? Well, it's a transition metal. Crap. Can't just look at the table and figure it out. So we look at the sulfur. Must be something we can do with the sulfur. Sulfur must be negative 2. Very good. Sulfur is negative 2 for a grand total of negative 2 charges. Now, the gold must bring a plus 2.
Yes.
But there's 2 of them. So every gold ion has what charge?
1.
Plus 1. Does that make sense? This is sometimes confusing for people. So the gold is called gold 1 sulfide. Okay? It's gold 1 because the gold has a plus 1 charge. Okay? So this is gold 1 sulfide. Be very careful on these ones with the crisscross. Yes, but yes you can. I'll show you in a second why you have to be very careful. Think of it as,
2, but then you put 1.
yeah, think of it like this. You can, what, you have a question? Oh, she has a good question. Let's listen to hers because this might help you. Why is it gold 1? Think of the molecule as a party. So think of the molecule like gold Au2S as a party. The positive charges are the ladies, because I don't want to call them the negative charges because I'll get beat up on Valentine's Day. and the negative charges are the men. And when you go to a party, it's good to have equal men and women, right? Let's just assume that's a good thing, okay? So now, the men, because we're cheap, we come to the party in the sulfur. We drive one atom to the party. So 2 negative charges come in the sulfur, right? The ladies, because they're rich and have nice cars, they come in separate vehicles. They come in a gold molecule, a gold ion each, right? So 1 plus charge per car. So far, so good? So then if you look at one of the cars, you would say one of those cars has 1 lady in it, so the car is positive 1, right? So it's gold 1 sulfide. Does that make sense? Does that help a little?
Yeah.
That's the most confusing thing. Well, one of the most confusing ones. All right? Is that a little better?
For the gold, or does it happen to another one also?
If any element, actually, it'll happen to. Any element. Okay? Is everyone okay with that? We'll do another example. Is everyone kind of okay with that? So it's gold 1 sulfide. Now there's 2 golds in the molecule. That doesn't matter. The charge on the individual gold ions is positive 1. That's what matters. Okay? Everybody okay with that? Sort of? A little bit?
Positive 2 is positive 1.
The gold atom, or sorry, the gold ion is plus 1, but there are 2 of them to balance the sulfur's charges. Okay? Let's try another example. This might be helpful. Let's say, so this is gold 1. Let me make this a little neater. Kind of got a little carried away with my writing there. So that's gold 1. Let's do one more example, and this might be helpful. Let's try that one, AUS. So instead of AU2S, now it's AUS. Okay? We don't know the charge in the gold. Let me write the name here, though. Sorry. Gold 1 sulfide. This one would be AU. We don't know the charge, but we know sulfide has a negative 2 charge, right? Now, on this molecule, AUS, only 1 gold ion comes to the party. We know that the sulfur brought 2 gentlemen to the party, right? We know that. The ladies and the men have to equal, so the gold must have brought how many? 2. So the gold must have positive 2. So there's 2 ladies in the car. So that's gold 2 sulfide. Make sense? Because with the metal charge is plus 2 there. So this one is gold 2. Okay, so gold 1, gold 2. The Roman numeral, again, corresponds to that charge right there. Does not correspond to that. Okay? So don't get that confused. That's the easiest thing to get confused by. Sound okay? Everybody? Everybody? Okay, good. Very good, very good. All right, let's, I don't want to do that one. Try that one. Name the following, FeCl2. Fe is gold, in case you don't know. I'm sorry, iron. Did I say gold? I wish iron was gold, man, I'd be rolling. Everybody get it? It's pretty simple, right? We went over this one already, actually, but it's pretty simple, right? So what's the answer?
Iron 2 chloride.
Iron 2 chloride. Makes sense, right? The idea makes a little bit of sense. Oops. Try these two. SN, in case you don't know, is tin. And SN is one of those exceptions to the transition rule. SN sits outside the transition metal zone. But tin, SN, and lead must also have Roman numerals because they can be +2 or +4. So all the transition metals, plus tin and plus lead, SN and PB, must have Roman numerals as well. So SN is 10, it also gets a Roman numeral. So does lead, PB. The top one's a little tricky, huh?
Mm-hmm.
Not too bad, though. You guys can do it. You guys are awesome. Those are sparkly. Those are sparkly. Look at that. That's cool. Wish I was cool. How's everybody doing? Horrible. Oh, someone's honest. I like that. Honesty is the best policy. Because now I can help you. How's everybody else doing? Not so horrible, maybe worse. Don't worry. This stuff gets easier as you try it. It doesn't get harder. On the iron one, right? Yeah, the other one's easy, right? What?
Is it gonna be iron 3 oxide?
Can't tell you that. People are still working. But I wouldn't change my answer yet, though.
When it has those two numbers, it confuses me.
Yeah, I know. It confuses everybody. That's why we're doing them as practice. All right. So you want me to do them, or at least want me to go over them?
Yes.
All right. Now the top one is by far the hardest one because, as you pointed out, there's two numbers, but they're not that challenging. There's two ways to look at it. And it depends on who you are, which one you like the best. It doesn't matter to me how you do it. Fe2O3. So now we have 2 irons, yeah? And 3 oxygens. Each oxygen is -2 for a grand total of -6. So the oxygens, the gentlemen are driving to the party in 3 separate cars, 2 guys per car, right? That's what that means. So now, in order to balance out the party, we must have 6 ladies. So there must be 6 positive charges come to our party. The ladies came in 2 cars. So how many ladies per car? 3. So the iron is +3. +3 and +3. So the name of this molecule is iron, Roman numeral 3, oxide. Because the plus charge, the iron is +3 charged. So the Roman numeral, please keep this in mind. The Roman numeral comes from the charge on the metal. You cannot, for this example it worked out, but you cannot always just look at the counter ion and say it's +3, it's negative, it's +3 or +2. You can't always do that. And the next one is an example. Well, not the next one, but I'll show you an example of where you can't do that. Okay? Everyone get that one? Everyone okay? You see how I got that?
Yes.
All right. Here's another way. It may be a little easier for some people. And someone already mentioned it, so now I'm going to show it to you. Remember last time we did a little crisscross? Like that, and the charges go away? You can do what's called a reverse crisscross. What you can do here is take the numbers and go like this. And that will become iron plus 3, oxygen minus 2. Now, before you say, okay, it's iron 3 oxide, I'm good to go, check the charge on the anion. So the oxygen is minus 2, right? Everyone see that? The oxygen is minus 2. Check the periodic table. Oxygen, okay, oxygen should be minus 2. So that's right. What can happen is if you do the reverse crisscross, you'll get oxygen minus 1 or oxygen minus 3. They're both wrong. So something happened. The crisscross trick only works if you know how to use it. With great power comes great responsibility. No one thought that quote was cool? Yeah. Who said that? Anyone remember? Spider-Man, there you go. I thought someone was going to say Winston Churchill, but no, Spider-Man said that. Well, it was his uncle, wasn't it?
You're right.
Uncle Ben said that, right? Anyway, so yeah, I'm a big nerd. So that's iron 3 oxide. Iron 3 oxide. Okay, so the crisscross trick is powerful. It can be used, but use it wisely. Now here's 2 examples where it falls apart. But I'll show you how to fix it. I'll show you how to fix it. What if we had this? Both of those molecules exist. Okay, the top one. We're going to do the reverse crisscross trick now. So there's an imaginary 1 there and there. Reverse crisscross it. You'd get Sn plus 1, O minus 1. Okay? Everyone see that? If you do the reverse crisscross on tin oxide, SNN, SNO, you'll get oxygen with a minus 1 charge. Is that correct? Well, it's correct if we do that, right? But it's incorrect if we look at the table. Right? What's wrong with it? What? Oxygen should be negative 2. The crisscross trick says oxygen is minus 1. Is that correct? No. Oxygen should be negative 2. So this is not right. So the crisscross trick is lying to me. The crisscross trick wants me to say tin 1 oxide. But you know better, because you know oxygen should be negative 2. How do I make a negative 1 a negative 2? You multiply by 2. Yes? Multiply that by 2, multiply that by 2. It becomes Sn plus 2, O minus 2. Now that is correct, right? Everybody see how I did that? That's where the crisscross trick falls apart. So this top one is tin, Roman numeral 2, oxide. It is not tin 1 oxide.
So is that an answer to the first one, or are you just making it up?
I'm just making this up now to illustrate a point.
Okay.
Answer to the first one was iron 3 oxide. So that's the top one, SNO. SNO2, be careful with that one too. So this one, there's an imaginary 1 at this point. Let's do this in a different color. There's an imaginary 1 right here. Crisscross them. You get Sn plus 2, O minus 1. Oxygen is not negative 1. Oxygen is negative 2. Is that correct? Mm-hmm. So multiply both of them by 2 again. So multiply by 2. Just the numbers, I mean. You get tin plus 4, O minus 2. Is that the correct charge of oxygen? Yes. So this bottom one is tin 4. Tin 4 oxide. Okay? So you can use the crisscross trick if you like, but be very careful with it. Okay? If you use it wrong, I will mark you wrong. Okay? If you don't like what I just said here, then don't use it. Use the way we've always been doing it. I like to give 2 options to people. All right? So be careful with the crisscross trick. Say it after me. Be careful with the crisscross trick. Okay, no one wants to say it. That's fine. That's fine. But be mindful, if you do use it and you use it wrong, I'll just mark you wrong. I'm not gonna give you the benefit of the doubt. All right, let's do the bottom one now. SnCl2. SnCl2. Anyone got it? SnCl2. 10. So we have 1, 10, yeah? Cl, Cl, -1, -1. What's the total charge of chlorine, or negative? -2. So what must the charge on tin be? +2. So it's 10, 2 chloride. All right? If you didn't like the crisscross trick, use that. That never fails. The crisscross trick, I know lots of ways it fails. So you can expect to see those on the exam, right? I will give you ones that the crisscross trick doesn't work very well. But you can still use it if you understand it. All right. Oops. Yeah, that's right. Okay, good. Very good, very good, very good. Now, what if we want to go from a name to a formula? It's even easier, I think. A name to a formula, even easier. All right, so we want to write the formula for chromium-3 bromide. Chromium-3 bromide. So, we look at that name and we know that chromium is probably a transition metal. Why? Because it has a Roman numeral. Look at the table. It's in group 6, smack dab in the middle of the transition zone. So chromium-3 literally means Cr plus 3. That's chromium-3. Chromium plus 3. What's the charge on bromine? Bromine is -1. So now remember, the charges must equal. The negatives and the positives must be the same. So we have to do what? Have to have 3 total bromines, right? Br minus 1, Br minus 1 for a grand total of -3 from the bromine. Right? And the chromium brings +3. So that would be CrBr3. Easy, right? That's easier.
Repeat the +3 for chromium.
It says chromium-3 up there.
Oh, okay.
So it's +3 on the chromium. If it had been chromium-4, it would have been a +4 on the chromium. If it had been chromium-2, the chromium would have been +2. Okay? That's what that Roman numeral means. It's the charge on the metal. Easy peasy, right? Oops. So give these 3 a try. The B, the book says zinc doesn't get a Roman numeral. I say it does. B is zinc 2 chloride. So I'll write that down here. B, zinc 2 chloride. Zinc 2 chloride. And the rest of them are okay. Nickel 2 sulfide, zinc 2 chloride, iron 3 oxide. That's interesting. Yeah. And zinc is Zn, or Zn. Everybody got it? Probably, right? Confidence. You just say, yes, I have it. Simple. All right, let's do the first one. A, nickel 2 sulfide. So we have nickel with a Roman numeral 2 and the word sulfide. So nickel is Ni. If you have a periodic table with the names on it, so you'd know that. Nickel is Ni. So what's the charge on the nickel? Positive 2, right?
Yes.
Everybody? Positive 2. Nickel 2 means nickel with a plus 2 charge. Sulfide has what charge? Negative 2. So we have negative 2 from the sulfide, plus 2 from the nickel. That's equal. So it'll be NiS. Right on? Everybody get that? All right. Over here, we have zinc 2 chloride. So zinc is Zn, or Zn. What charge is on the zinc?
2.
Positive 2, yes?
Yes.
Everybody?
Yes.
And the chloride brings what charge? Chloride negative 1. So, that's not quite right then, because there's too many ladies, not enough men at the party. So, one more person shows up, brings negative 1, total of negative 2, positive 2. So that formula is Z, or ZnCl2. Pretty simple, right? So far? And the last one. C. What do we got? Iron 3. So the charge on the iron is? Fe is plus 3. Very good. Start again. Here we go. Draw an F. Fe plus 3. O is negative 2. Right? Ooh, that's a little trickier because they're not even. Iron's got a negative number. Well, in order to make this party work, we know that 3 and 2 will divide into what number evenly? 6. So we got to bring 6 ladies and 6 men to this party. So to get 6 ladies, because ladies are carpooling very well, Fe plus 3. So another car shows up with some more ladies. So we get a positive 6 ladies at our party. The men, because they like to drive their Mustangs, negative 2, for a total of negative 6. Right? So that's 2 irons and 3 oxygens. So Fe2O3. Those are your answers. Okay? Not too bad, right? Not too bad. Alrighty, let's keep on trucking. Very good, very good, very good. Write this word down. Polyatomic ion. Polyatomic ions. Polyatomic ions. Does anyone know what the prefix poly means? Many. Polynesia. Many. There's other poly words I can use, but I will not. Many. What's atomic mean? What's atomic energy mean? The atomic word in atomic energy means atom. Okay? So polyatomic literally means many atom. What's an ion? It's a charged particle. An ion is a charged particle. Cations are positive, anions are negative. So this phrase, polyatomic ion, means many atoms charged. That's all it means. So it seems complicated, but it really isn't. It just means many atoms with a charge. Okay? Now, if we look at these, forget that. Let's just move on. Whoops. If we look at some examples of polyatomics, we see here there's printed 6. Concentrate on the first 3. The first 3 are very common. Very common. In fact, I have a feeling, well, I know for a fact, I would say all of them have involved your daily life. And you're like, ew, I don't deal with chemicals. Yes, you do. Okay, let's look at the first one. Sulfate, SO4 minus 2. Now, look at the SO4. Don't worry about the minus 2 just yet. The SO4, is there more than one atom there? Yeah, there's more than one atom there, right? There's 1 sulfur and 4 oxygen, so there's 5 total atoms, right? So that's many. Poly, right? And there's a bunch of atoms there, right? So it's polyatomic. There's a -2 charge, so it's an ion. So that's a polyatomic ion. Make sense? Now oxygen on the periodic table, just oxygen by itself with a -2 charge, that is just an ion. That is not a polyatomic ion. That's only one atom. This has got a whole bunch of atoms, so it's a polyatomic. Okay? Now the polyatomics are never, ever, 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 ever on the periodic table. Okay? Because the periodic table is just all the elements. Polyatomic ions are atoms that are put together that make a charge. Make sense? A little bit? So you won't find them there. They make themselves. Okay, SO4, that's a sulfate. And you're all thinking, when have I ever used sulfates? Do y'all have walls in your house? Yeah. Some of them are probably made of cinder block, but the other ones are probably made of drywall. Sulfates. Drywall is made of sulfates. Because sulfates don't dissolve in water, which is a good thing. Well, they usually don't. Shouldn't say they all don't. Phosphates. You're all like, I never use phosphates. Phosphates are polluting. They ruin the environment and blah, blah, blah. And they do all of that. I'm not saying they don't. Phosphate. Where do you see phosphate a lot? You ever drink a Coca-Cola? Read the ingredients. Phosphate. Big part of Coca-Cola. And Pepsi. Nitrates. So this is phosphate. Nitrate. Nitrate. Ooh. Nitrate. I don't eat nitrates. Those are bad. Most food has it in them, actually. Nitrates are a very strong preservative. Also, fertilizer. If you eat anything that's been grown, they dump nitrate fertilizer on it probably to make it grow. Nitrate's a very good fertilizer. It also makes things go boom too. It also is explosive. That's why you don't ever mix diesel fuel and fertilizer. But anyway, unless you're Timothy McVeigh. If you don't know who that is, look him up on Wikipedia. Okay, so those are three of by far the most common polyatomic ions, and these are called the 8 ions. Now, don't try to memorize these things. I'm going to give you a list of them, so your life will be a little bit easier. Other professors make you memorize this garbage. I don't, because there's a lot of them. You just can't memorize them all. But I would recommend that you memorize these 3 at least, because these are so common. You're going to see them all the time. Memorize at least those 3. There's a few more that I'm going to point out that you probably should commit to memory, but they'll all be on your little table that I'm going to give you. But flipping back to a table every time you need to know something is never a good idea. It's always good to have some things in your memory so you just know them. Like sulfate, SO4, -2, just know that. Phosphate, -3, just know that. Nitrate, -1, NO3, just know that. Those are some good ones. There's the ite ones down here, SO3, PO3, NO2. Notice, just real quick, look at the sulfite, the SO3 -2. Notice the one on top, SO4 -2, sulfate, SO3 -2, sulfite. The ites have one less oxygen. It's weird, I know. So ites have one less oxygen than the 8s. So nitrate is NO3, nitrite is NO2. Subtle, very subtle. I don't make you memorize that. I will show that to you. I'll give you a table on your exam. All right, here's a few more. Here's a couple that I would like you to commit to memory. Cyanide, CN-1. Now, why do I want you to memorize cyanide? Because this is freaking cool. This is cool. Cyanide's cool. Why is cyanide cool? Because you hear about it all the time. Oh, cyanide poisoning, especially in the movies. Cyanide poisoning. It's not funny. Someone died. Anyway, cyanide poisoning. That's a very common thing to hear about in the media, especially because people sometimes die from it. The cool thing about cyanide is that if you treat it with acid, you get this thing here called HCN. I won't draw that, just HCN. That's called hydrogen cyanide. That actually is a gas, and it actually smells like almonds. It smells really, really nice. This will kill you in a matter of seconds. You got maybe a minute, and then you're going to drop and die. And I don't think there's any coming back from it. How do I know it smells like almonds? Because I smelled it by mistake. I was working in a lab, and I was young at the time. I was probably only 20. And I know you guys are thinking, oh, I'm 20, I'm not young. Yeah, you're young. I was 20 years old weighing out some sodium cyanide, or potassium cyanide, KCN. So I was weighing this stuff out. And I knew that KCN was dangerous if I ate it. so I wasn't going to eat it. I was just going to weigh it out. What I didn't know, because I was young and stupid, was that when you weigh this out in the atmosphere is full of water, right? So the atmosphere is full of water. As you weigh this out on the little dish, you got a little pile of crystals here, right? There's a word called hygroscopic, which I knew about but never respected until that day. Hygroscopic means material will draw water from the atmosphere. So you have a little material sitting on your counter, and it will slowly bring water into itself because the water is in the atmosphere. It'll go into your whatever's on the table. So as soon as that happens, some water hit my KCN. So water plus H2O, or water. And then all of a sudden, gas. Can't see it. Just gas came off that stuff. You couldn't see it. You couldn't see any of it. But God, did you ever smell it? And did it ever smell good? Like you wanted to breathe it. Like you were like, oh, that's great. But luckily I was smart enough in my early 20s to know that I smelled almonds weighing out potassium cyanide. I'm breathing in that gas. I probably should put it in the fume hood, which I did. And then I went home because I had a blistering headache. It gives you a blistering headache. Then it kills you. Ta-da. I'm still alive though, thank the good Lord. But yeah, that was dumb. So anyway, cyanide. That's fun, right? Cyanide is a good time. If it's not you. OH. Now, memorize that one too. OH minus. These are just some common ones that you're going to see. Again, they will be on your formula sheet. But these are just ones that I put on the exams all the time. Like, these are very common. Sulfate, phosphate, nitrate, hydroxide. Very common. You can find that in your house probably. That's Drano. Sodium hydroxide is an example. Drano. Ammonium. Ammonium hydroxide. Ammonium, NH4. Another one I want you to memorize, and put a box around this one and a star and maybe a couple of exclamation points, and maybe put, interesting and probably on the exam. This is ammonium. Ammonium. That is the only polyatomic cation. In this class. There are many polyatomic cations, but the only one that we're going to learn about is ammonium. And that you can find probably under your sink if you're still clean with ammonium. It's usually called ammonia in homes, but it's actually ammonium to a chemist. So that's a bathroom cleaner. Kills bacteria and all that kind of stuff. Smells like urine. Smells really bad. But it cleans really good. So those are some common ones, and that is the only cation that we're going to see that's a polyatomic. Okay? So far so good? Okay. Now, the carbonates. Those are interesting. Let's talk about those a little bit. Those are fun. Carbonates, CO3 minus 2, and then H, CO3 minus 2, minus 1. That's carbonate. That's hydrogen carbonate. Also called bicarbonate. So both of these names are correct. That's called hydrogen carbonate or bicarbonate. Either one is correct. Those are fun. Does anyone know why? They don't blow up or anything. No one knows why? Really? Usually somebody knows. Anyone like to bake? Any bakers? 1, 2. None of y'all bake? No. Here's your assignment for next week, because I'm not going to be here. After your 3 hours with the tutor, go home, make a batch of cookies. No, seriously, chocolate chip or oatmeal raisin, and then bring them in the week after and give them to me. We don't have class the week after, so there, haha. Anyway, well, no, we do. There's an exam. No, don't bring me any food. Don't bring me any food during the exam, because you're all going to poison me with cyanide. Now, has anyone ever heard of baking soda? This is baking soda. Usually it's called bicarbonate of soda. Hold on a sec. That's its old-fashioned name. Your grandmother probably called it bicarbonate of soda, or soda. Okay?
I'm not so sure, but the HCO3 is not on the pH scale
Sure it is.
when it's alkalitic.
Yeah, it's like pH 10.
Yeah.
Yeah.
Something like that.
Yeah, it's very basic. Yeah.
Can you make your own baking soda?
It'd be difficult, but yeah, you could do it. It's cheaper to buy it, though. Stuff's not expensive. Okay, so this is baking soda or bicarbonate of soda. You throw that into your cookies and cakes. This is a chemical leavener. You don't have to write that down. I was going to write it down, but you don't have to. It's a chemical leavener. There's two kinds of leaveners in baking. Leavener just means to rise, makes things rise, like bread. You know, you make bread and it rises, right? That's called leavening or rising. In bread, it's usually yeast. People use a biological leavener, so it's yeast. The yeast goes in there, eats the sugar, and then poops out CO2. Don't laugh, it's true. And then chemical leaveners, they react with acids and make CO2 to make your cookies go nice and fluffy. You know what I mean? Everyone likes a fluffy cookie, right? And your cakes too. Okay, so that's how that works. And carbonate is usually in things like, what is it, Alka-Seltzer? Plop Plop Fizz Fizz, Alka-Seltzer. That's what, and Tums is usually carbonate too. Any kind of anti-acid is a carbonate, typically, not always, but typically. And then there's sulfate and bisulfate. They're not quite as interesting, so I'm not even going to stop there. Just going to move forward off of that. But the baking powder, that's pretty cool. You know why? Because you eat it. Here are 4 you don't really have to write down. There's only one of them I want you to write down in your notes. ClO, hypochlorite, hypochlorite or hypochlorate? Hypochlorite, okay. ClO, that's bleach. And you buy bleach at the store, you buy sodium hypochlorite. That's what makes the stains go away in your clothes. It's also what if you have a pool and you have a normal chemical pool, that's what they dump in your pool. The pool guy comes with the big old yellow jugs and dumps it in your pool. That's what he's dumping in. Kills bacteria and fungus and mold and all that kinds of stuff. Kills pretty much everything. Makes your hair frizzy, makes your bikini and your swimsuit get all weird, and then eventually it ruins it. Okay, so let's talk about compounds with polyatomics. The rules don't change. The rules don't change. Naming with polyatomics is the same as naming with normal ionic atoms. The only difference is now you have these NO3s and NO4s or NO2s and whatever to deal with. That's the only difference. So here, let me show you how to do it. It's very easy. It's very easy. Very easy. Repeat after me. It's very easy.
Very easy.
Thank you. All right, we're going to write the formula for magnesium nitrate. So we have magnesium, and a nitrate is NO3 minus 1. You'll be given that on an exam. You will know that nitrate is NO3 minus 1. It'll say it. It'll be NO3 nitrate minus 1. It'll tell you. It'll be very clear. Okay, so now Mg is bringing plus 2 to our party. NO3 only brings minus 1 at a time. So how many NO3s must we have?
2.
We must have 2 of them, right? So 2 NO3s. Negative 1 for a total of negative 2. That's not anything major, right? Everyone agree that's not anything major? So how many nitrates are there? There's 2 of them total, right? How many magnesiums? 1. So it's Mg NO3 2. Now here's the problem that you have to remember this. We have this 2 and that 3 kind of sticking together, and it kind of looks odd. So put a parenthesis around the NO3. That parenthesis means this is a group, and there's 2 of that group. Does that make sense? Everybody okay with that? There's 2 of that group, 2 coming. That 2 means there's 2 of these, and there's 1 of those. Not hard, right? Now this is bigger, okay? Not hard, just bigger. So don't think it's hard, it's just bigger. All right, so we can do some examples. Oops. Select the correct formula for each. Now, ammonium nitrate. Now, you don't know this, so I'll tell you. Nitrate is NO3 minus 1. Nitrate is NO3 minus 1. Hydroxide is OH minus 1. So let me write that up here. And you guys can give these a shot. The only thing different here is now you have polyatomics. And hydroxide. Okay, so that's the only difference. So give those a quick shot. They're not difficult. I'm sure all of you guys will get this pretty quickly. At least you better. Time. Oh, goody. How do we do? Good? Excellent. Glad to hear that. Everybody else? Still hammering. Good, good, good. Now what? Good? One person, two people. 3 people. I'll take that as a yes. I'm going to do it anyway. I don't want to stand here anymore. Standing here makes me nervous. All right, let's take a look at these up front here. Aluminum nitrate. So what's the formula? What's the symbol for aluminum? Al. And what's the only charge aluminum can be? Positive 3. Remember, aluminum is the only one we talked about that had a +3 charge. Okay, so now nitrate is written right there. Nitrates are NO3 minus 1. So NO3 minus 1. Okay, So to this molecule, aluminum is bringing +3 charge, so the nitrates must bring a total of -3, right?
Yes.
Right? So there'll be NO3 minus 1, NO3 minus 1 for a grand total of -3, and the aluminum brings the positive. So this will be Al, open parentheses, NO3 to the 3. Have to have the parentheses there around the polyatomic to indicate that there's 3 of them. Okay? Is that okay? Seems all right to everyone, right? All right, the next one, copper 2. So what's the charge on copper? Positive 2. Very nice. And the NO3 are negative. So how many NO3s must there be here? 2, right? NO3 minus 1 for a grand total of -2. Copper is positive 2, so this would be Cu parentheses OH parentheses 2. Oh, NO3. Sorry. I'm thinking of the last two already. Sorry. My mind gets ahead of me sometimes. There you go. Sorry about that. NO3 minus 1. So it'll be total of 2. Cu, open parentheses, NO3, close parentheses, subscripted 2. Subscripted 2. What else we got? Iron 3 hydroxide. What's the charge on the iron?
3.
Fe plus 3, yes? Everyone gets that part, right? Yeah? Okay. OH, or hydroxide, excuse me, is OH -1. So iron brings +3. The OHs must bring a total of -3. So there must be 3 of them. That make sense? Everybody likes that? It's the same as always, right? Fe parentheses OH close parentheses 3. So far so good, guys? And the last one, tin 4. So what's the charge on the tin? 4, right? Positive 4? Everybody? So the last one, let me just draw a quick line down here. Sn plus 4, OH minus 1. Tin brings a total of positive 4. The OH must bring a total of -4, so there must be 4 of them. Make sense? So the formula here is SnOH 4. Okay? Everybody happy with that? Yeah, go ahead.
So aluminum is the only one that you just have to know that is positive.
Yeah, that's the only positive 3 ion we talk about in this class.
Okay.
Yep. So if you look in group 13, it's a metal in group 13, so it's the only one that has a +3 only.
Okay.
The other ones below it can be more than +3.
All the other ones that you're going to give us are going to have like the iron 3s, so we'll know the pop, like the charge.
No, only the transition zones in tin and lead.
Okay.
So if it's a transition metal or tin or lead, you'll get a Roman numeral. If it's aluminum or magnesium or sodium or calcium or whatever, calcium's in group 2, so it has a positive 2, right? Lithium's in group 1, so it's positive 1, right? So those ones you know. All the group 1, all the group 2, and aluminum you know. The transition elements you don't know, and tin or lead you don't know. So you have to use the anion to tell you. Make sense?
Yeah.
Anything else? All right, come back in 10 minutes, please. We'll take a quick break. Oh, here are your quizzes from last time. I want to pick them up. Take a break. Huh? No, I'm not allowed to. I have to hold on to them for a year, so I'll give them back soon.
It's a credit card company that they just call to make payments, ask what's their balance, and activate their credit card. Did anyone tell you that? No, they don't. They just call for an account. Oh, they didn't go on the insurance? Oh, no. I guess the people that comes early, definitely comes late, because these people that person was there very early,
I think probably like a few people they said to me, they didn't, probably didn't need too much spots for that, but.
Yeah, so I'm just like,
It's not alright, but if I don't get my car by this week, I'm gonna go to work at 1. Because I got to school at 12 and I work at 1. When I take a break, I'm not going to work. I'm just getting back to that. I need a car, a reliable car. Oh, and then my son car? I'm not trying to get like you don't have to sell it, you don't have to sign a contract saying that in 6 months, if anything goes wrong with the car, like big major problems, then they don't want you to want. I really don't. I don't I mean, yeah, but there's some good cars, you know, if they fix up the car right and everything like that. No, I don't have time. I really don't have time. I don't have time to just open up the job. To do it without I really need more. No, yeah, actually, my new bar is changing. I go to work from 4 p.m. to 12. To 12. 4 p.m. to 12:30 a.m. And starting next week, I'll be going to work from 1 p.m. to 10:30. So I really need a car accident. Maybe you go to the car, cheap car. I just want to pay everything like $1,500. I want to get a B4. A B4 is good on gas. I don't need someone that be a gas car, B8, B6. Like, so there's 6 I want to get so that's what I got. You should get my number so tell me you need to put out here. But I don't practice, so I have to get home to work. So everybody's like, oh God, and I'm like, yo, let's be first. I can't do that, so it's not right. I'm gonna go. It's your life. And you are? Nadia Chem. I don't regard your name. Nadia Chem. L-I. Not Y. You not put the Y. I know you did. I didn't get no call.
All right, guys, we're back in session. Go ahead and try that problem on the overhead. Take 5 minutes to get those answers cranked out. SO3 is sulfite. SO4 is sulfate. ClO3 is chlorate. Brian. Did you guys both do those problems? Okay, make sure you get them done. Not hard, right? The hardest thing is just knowing their polyatomics and looking them up on the table. That's the only hard part. They're the same as all the other ionic compounds. Nothing different. Nothing different. Just that pesky polyatomic. But you'll have the list of them on your exam. The list is actually in your textbook. Let me just grab that book from you real quick. Let me tell you what page it's on. The little table that I will give you on your exam is found on page, let me find it first, page 138, table 4.7. I will give you that exact table on your exam. Page 138, table 4.7. I'll give you that exact table, only bigger, on your exam. So you don't have to memorize it. Now, please, 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 please do enough problems where some of the more common ones become second nature. Like sulfate. Sulfate's, it's in a lot of things. Like it's just a very common one to talk about for whatever reason. So please, some of them you just want to know. Some of them you may have to look up. Like chlorate, you probably don't have to memorize that. But you probably also won't see it on an exam either because it's kind of odd. You know, it's just not that common. All right, did y'all get them? Yeah. What's the first one? Magnesium sulfite. Magnesium sulfite, very nice. And the next one?
Magnesium sulfate.
There you go, see? Put that emphasis on the 8 there. Good. Magnesium sulfate. And you know what is really kind of funny? If you're in a lab with some chemists and you're talking about stuff, and this happens all the time, people will be saying sulfite and you're hearing sulfate, so you say, you mean sulfate? They go, no, sulfite. I said, okay, sulfite? No, sulfate. And it'll go like that for a minute until we write it down. No, I mean this one, SO3. Oh, okay, sulfite. That's what I've been saying. Why don't you say so? You know, it's kind of funny. Chemistry humor. Anyway, what's the bottom one? Why isn't it calcium 2?
Because the 2 it's only for the chlorate. That's what you said. It's only.
Right, but we know the calcium in this formula has a +2 charge, right? So why wouldn't we say calcium Roman numeral 2?
Because chlorate is not a transition metal.
Very nice. It's not a transition metal. It's in group 2, right? So all group 2 metals have what charge? +2. All group 1 metals have what charge? +1. What's the only metal with a +3 charge? Aluminum. Very nice. So it's not hard. It's not hard. Yeah?
So for the first one, would you would the number be 6? Like Roman numeral 6 in the middle?
For the first one?
No, I'm just saying if you were to put it, for some strange
Not for these ones, because magnesium and calcium are both group 2 metals, so they don't require Roman numerals. Only transition metals and tin and lead require Roman numerals in this class. Okay? So only transition metals, tin and lead, because tin and lead are
And the transitional metals are?
group 3 through group 12. Yep. Group 3 through group 12 are transition metals. Tin and lead are the exceptions. They're in group 14, but they're the exceptions to that rule. Because they can have more than one charge too. Very good, very good. Give these ones a try. Now we have a mixture of transition and non-transition elements. Oh ho ho ho. Not too bad though. Pick out the ones that are transition, pick out the ones that are not, and name them. And I'll give you the polyatomic names right here. Sulfate, you have PO3. What the heck's the charge on PO3? I don't even know. Must be -2. That one I gotta check the charge on that one. I may have forgotten. I think CO3. Let's check that real quick. It's phosphite for sure, but is it 3 or 2? -2, okay. Wait, no. -3, oh, okay. Wow. Did not know that. There you go. Ba is barium and Pb is lead, in case you didn't know. Again, you'll have a periodic table on the exam with the names written on it. Don't memorize them. So, how we do? Anyone know the first one? A?
Iron 2.
Iron 3. Iron 3. Let me write that down and then show you why. Don't forget the parentheses. Alright, so why is it iron 3, not iron 2? It's iron 3 because, if you look at that formula, Fe2O3, sorry, not O3, Fe2SO4 to the 3. That formula means there's 2 iron and 3 sulfate. We know sulfate has a -2 charge because it's written right here. So there's a grand total of -6. Is that correct? So the sulfates bring -6. That means the iron must bring +6. But there are 2 of them. So the charge in the individual ions is +3. So this goes with that. This does not go with that. That does not. The X to the arrow means it does not go with, or does not equal. Okay? Very common error on that one is to say iron 2 because there's 2 right here. Makes it seem really easy, right? But that's completely wrong. It's the charge right here that matters. Okay? So that's...
When you say number 8, can you just say the 3 is outside the parentheses?
It's a crisscross trick. Could be, but that does work, but you got to be really careful with it. I don't usually do it because it's like there's so many nuances to it. If you can get it to work for you, groovy. If not, use this way because this way never fails. The B, part B. Barium is Ba. PO3 is phosphite. So what is that name? Barium phosphite. Why isn't it barium 2 or barium some?
Because it's not a transitional element.
Right. Both answers are correct. It's not a transition element and it's a group 2 metal. So it's barium must be +2 because it's group 2. You only need a Roman numeral for transition plus tin and lead because they can have more than one charge. They can be +1 through positive, some of them are +6 or 7. Very nice. So that's barium phosphite. No Roman numeral required. Very nice. And the last one, C. Pb is lead. CO3 is carbonate. What would you call that?
Lead 1 carbonate.
The answer is lead 2 carbonate.
How do you get lead to?
Hold on now. Give me a second. So there's 1 lead in this molecule, right? And there's 1 carbonate, CO3. Run over here, we find that carbonate is -2. So carbonate is bringing a -2 to the party, so the lead must have brought a +2. This number right here goes with the 2.
That is PB, right?
Yep. There's-
PB.
oh, that's palladium, sorry. There you go. So that lead, 2 goes right there. The number 1 right here does not go there. Okay? That 1 is what, that gets a lot of people get that wrong. Do not get that wrong. The 1 does nothing to do with that. It's the charge. The charge on the metal. Okay? Everyone got that straight now? Yes? It's the charge in the metal, right?
Yes.
Everybody, wake up now. Come on. There's an exam when I come back. So,
Yes.
is that true? So it's the charge on the metal, not how many metals there are. Which one? I didn't hear the question because people were murmuring over you. What did you say?
Like on A and B, I get confused to why they have the 3 and the 2 outside of the parentheses away from.
Right, okay. The SO4 is a unit. So the SO4 is 1 unit by itself. So it's a car all by itself. It's a big car, but it's a car. Okay? So it's saying that there are 3 of those SO4s are coming together to the party. Make sense?
Okay, but then they use that 3 for the iron.
That's the crisscross trick. Hold on now. You're using the crisscross trick to figure out the charge in the metal, which you can do, and it often works, but it often falls apart too. So you could do that, yes. But that 3 in that formula, all that 3 means in the formula is that there's 3 SO4s.
So I would write SO4 2 times.
Yes, you would. SO4 minus 2 3 times.
And the PO3, I'd write that twice.
Write that twice. And then for the iron, in the top one, the iron, there'd be 2 irons. Okay, that's all those numbers mean. Now, you can crisscross trick it, and sometimes it works out that the numbers on the subscripts are the charges. Sometimes that does work. Sometimes it does not. And I know all the times it doesn't, so I will show those to you a lot. Because the crisscross trick doesn't tell me that you know what you're doing. It just means you can move numbers. Okay? I'm more about, do you understand what you're doing? Okay? So be mindful of that. I personally would just do it the way I do it here. It's longer, takes a little while, but just do it. Seriously. Because you can't be wrong doing it this way. Crisscross trick. I tell people every year, I'm going to give you the ones where the crisscross trick doesn't work so well, and every year people try to apply it, and every year they get it wrong. So I would just do it this way. There are some professors who don't even teach the crisscross trick because students just use it wrong. So I teach it because some students get it, but if you don't get it, don't use it. All right, here we go. This is a lot easier than what we just got done, so you'll be happier now. Covalent compounds and their names. Now, covalency is fun. Covalency is fun. Why? Because things are attached now. Things are attached. Ionic compounds, they're interesting and they're fun. They taste good in potato chips, but they're not attached. So remember, did we do a little demo here last week? Wasn't there someone up front here with me? Or was that a different class? I get confused in all my classes. We had ionic compounds versus covalent, right? Ionic compounds, you give electrons away. So now covalent compounds, let's just, Maria, right? You sit right there. Maria and I, we're going to just do a quick demo. She doesn't have to stand up. She can just sit down. You know, it's Valentine's Day. You know, treat the ladies nice, right? All right, so Maria has an electron, and I have an electron, okay? Now, we're both nonmetals. In covalent compounds, both atoms are nonmetals. So I'm a carbon, she's a carbon, let's say. Or I'm a hydrogen, she's a carbon. Doesn't matter, just nonmetals, okay? I am looking for an octet. She is looking for an octet. With me? So, in ionic, I would just steal it, right? But now that we're both kind of the same, we're both kind of the same ability to steal electrons, I come to steal hers, and don't let go of it. You try to steal mine. Ugh. And now we fight. Now everyone says, oh, this is a sharing, like it's all, oh, you can have it. No, I can have it. No, they're fighting for it. Both atoms are pulling. What'd you do? There you go. Try that again. Okay, so she's trying to pull mine. I'm trying to pull hers away from her. And that little battle we have going on will never end until something else happens. Until another atom comes along and makes us react, or until someone lights us on fire, or whatever. We will always struggle for these electrons. Okay? Now, if I walk over here, don't let go. Maria's coming. I'm dragging her along. If she goes over there, I'm coming with her. Why? We're physically connected. Okay? Make sense? Yeah. This is a physical connection. We are touching. Okay? Another way to do it is I grab her arm, she grabs mine. We're connected now. I want to go over there. She's coming. She can't stop. She can't make me not go there. If she wants to go over there, I have to follow her because we're physically connected by a rope, let's say. Now in ionic, she stole my electron. I'm positive, she's negative. In a solid form, we're side by side. We're not actually connected, but we're side by side. Dissolve us in water, I'll go over there, she'll go over there, right? In covalent compounds in water, she goes over there, I'm going with her. I go over there, she's coming with me. Okay? We're physically connected. She's trying to steal my electrons, I'm trying to steal hers, we're fighting. In ionic, she just wins and I just lose. Okay? Positive, negative. With me so far? Yes. That's the big difference. Thank you, Maria. Yeah. That's the big difference between covalency and ionic. Okay? Now, in ionic compounds, remember, it was a metal to a nonmetal. In covalency, it's a nonmetal to a nonmetal. Okay? So if we look at the periodic table, and I said, okay, oxygen is going to bond with nitrogen. They're both nonmetals, right? So they're going to make a covalent bond. Chlorine is going to bond with sulfur. They're both covalent, so they're going to, they're both nonmetals, so they'll make a covalent bond. Right? Mm-hmm. Hydrogen is way over here. Now it is in the metal zone, but it's the exception to the metal rule. It's a nonmetal. See how it's red? All the gases are red. So hydrogen is a gas, so it's definitely not a metal. Metals are solid and gray, or liquid and gray, or yellow for gold, or yellow for copper too, I guess. But hydrogen is a non-metal. Okay? It has one valence electron, that's why it's over here in group 1, but it is definitely a non-metal. So if hydrogen bonds to carbon, which is a very common thing, that's a covalent bond. They're trying to steal from one another. Okay? Everyone okay with that? Which part?
The hydrogen and
What's that horn? Happy Valentine's Day. Hydrogen is a nonmetal. Hydrogen's a gas, so it's a nonmetal. If hydrogen and carbon make a bond, they make a covalent bond, not ionic. Because hydrogen, even though it's in the metal area, it's a gas, so it's a nonmetal. The reason why they stick hydrogen in group 1 is not because it's a metal, it's because it has one valence electron. Okay? That's why it's in group 1. Some periodic tables actually put hydrogen in the center. They don't put it in any group. But it has one valence, so it's in group 1.
So in other words, nonmetals and metals is a covalent?
Nonmetals and nonmetals make covalents. Metals and covalents make ionic. Sorry, I got my words confused now. Metals and nonmetals, ionic. So barium and chloride, for example. Carbon to hydrogen, so nonmetal to nonmetal, covalent. Covalent.
What did you say in a second?
Nonmetal and nonmetal make covalents. Okay. So carbon, if carbon bonds to carbon, it's covalent. If carbon bonds to oxygen, it's covalent. If carbon bonds to hydrogen, it's covalent. They're trying to steal from one another. They're not actually stealing because they're not strong enough. If you bond a metal to a nonmetal, say lithium to chlorine, that's an ionic bond. Metal to a nonmetal. Okay? All right. So far so good, right? So now, let's talk a little bit about some nonmetal stuff. Here's that word, sharing electrons. Covalent compounds and when atoms share electrons to complete octets. Now, you can think of it as sharing. I think of it as attempted theft because they're trying to steal from each other, but they can't, and I'll show you why I say that later on in this chapter. And they're between nonmetals and nonmetals. So when two nonmetals bond together, say, I don't know, sulfur and fluorine, that's covalent. They're trying to steal from each other. Those are covalent bonds. And the groups 14 through 17 plus hydrogen do that, the nonmetals in those groups. The metals in those groups don't. All right, pretty simple, right? Nonmetal to nonmetal makes a covalent bond. Metal to nonmetal is ionic. Right? Those are just the rules. All right, let's talk about hydrogen real quick. Hydrogen is in group 1. Hydrogen has how many electrons? 1. Hydrogen has 1 proton, 1 electron. There we go. So there's 1 hydrogen. Now, hydrogen very much wants to have the same kind of electrons as helium because that's its corresponding noble gas. Right? So there's hydrogen way over there on the left, helium way over there on the right. That's period 1. Hydrogen wants to look like helium. Everyone accept that? Hydrogen does not want an octet. He's the exception. He wants a duet. He wants 2 electrons. Okay, that will fill his octet, right? Or, sorry, fill his valence shell. Is that correct? Everybody accept that? So hydrogen just wants 1 more electron. So what happens then? If another helium atom kind of happens by, helium, hydrogen. Man, I'm getting my names all confused today. Must be the love in the air. Now, they come by each other. So this Maria will help me out again here. Here's Maria. She's got her electron. I better give you that and you'll make your fingers all green. She happens by, I happen by. We try to steal from one another. Okay, so now we're tug of warring. I can't steal it, she can't steal it. But now, if you just look at Maria and ignore me, I'm still here, but ignore me. How many electrons does she have? 2. Ignore her now. Not that you should ignore Maria, but ignore her now. Look at just me. How many electrons do I have? 2. So that's why they call it a sharing. So at any given time she has them, at any given time I have them. That's why they call it a sharing, but it's really a, come on, give me that, I want it. Okay? You with me on that? So now, her valence shell is filled, and my valence shell is filled. Does that make sense? That's how covalent bonding works. We're trying to steal from each other, so at any given time she has them, or I have them, depending on how you look at us. Does that make sense?
Yes.
Thank you. That's all I got to do is break the bond. Just give it a little wiggle. All right. So here's Maria. We'll make Maria red, and I'll be the green one. So now, we wander by each other, and we say, hey, 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 I like those electrons. And we'll start to pull away from each other, pull the electrons away from each other. So here's me with my electron. And here comes Maria with her electron. And that's that's supposed to symbolically represent us fighting for the electrons. Okay? So now, with your hand, cover up Maria. Look at my hydrogen. How many electrons does my hydrogen have? 2. That satisfies its valence shell. Cover up me. How many does Maria have? 2. So that satisfies her valence shell. Her valence shell is full. She's happy. I'm happy. Everyone's happy. So now, we represent that like this. Because that looks funny. Let's represent it like this. H, H, and a line. Okay? Now normally it would be all in the same color, but I'm trying to emphasize a point here. That line between the two atoms represents a single bond. And that's 2 electrons. 2 electrons. Let me spell that out for you guys. Two electrons. So this here, these 2 electrons right here, represent that. Okay?
So a single bond will always have 2 electrons?
Always. Always. Very good. A single bond always consists of 2 electrons. So when you see this written, think, it's a line, obviously, but think of it as 2 electrons. Okay? Think of it as 2 electrons. Maria's got them. I got them. Now, cover that up. Cover up the red hydrogen. How many lines to hydrogen? How many lines? 1 line. How many electrons per line? 2. How many electrons on the green hydrogen? 2. Cover up the green one. How many lines to the red hydrogen? How many electrons per line? How many electrons does that hydrogen have? 2. Exactly. You got it. Okay? That's how we draw structure. And that's how we represent them. And that's how we try to get the octet or the valence shell satisfied. Okay? Now, that's what hydrogen looks like. This is hydrogen. H2. Hydrogen. If you want to buy a tank of hydrogen, you can. It's available commercially. You cannot buy H. You must buy H2 because H does not exist. Hydrogen H does exist, but it's always bonded to something else. If you buy pure hydrogen, it comes to you as H2. Okay? And this is why. Because the hydrogen must have a complete valence shell, and if you purify it, you'll actually get 2 H's bonded together because that satisfies their valence shell. Okay? Does that make sense? All right. So that's hydrogen. Pretty neat, huh? See? That's excitement right there. I like that. That makes me feel good. Let's do fluorine. Why not? Before we do fluorine, let me just say one thing. Now, this is stabilizing. Having a complete valence shell is a stabilizing effect. Now, don't confuse the word stabilize with stable. They're not the same. A stable molecule is like water. Water is everywhere on the earth. It's not reactive really. It doesn't do a whole lot. It's necessary for life, but it doesn't react a lot, right? It's stable. Hydrogen is stabilized, but that will blow up. If you light that on fire, it'll detonate. It'll big fireball. It's awesome, by the way, but that's what it will do. Okay, so it's stabilized. It's not stable. Does that make sense? Okay. All right. Let's do fluorine. Fluorine is fun, and I'll tell you why in a minute. Okay, let's look at fluorine. Fluorine's in what group? Group 17. So how many valence electrons does fluorine have? 7. Very nice. So let's draw those 7 electrons around the fluorine. 1, 2, 3, 4, 5, 6, and 7. Now let's draw a green fluorine. 1, 2, 3, 4, 5, 6, and 7. Okay, neither fluorine has an octet. Is that correct? So they want to have octets. Fluorine wants to look just like neon in terms of its electron configuration. So this fluorine wanders by that fluorine and they say, hey, 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 don't mind if I do. They try to steal each other's electron. But they can't because they're actually the same in strength when it comes to theft. criminal masterminds. And they have to forever compete for that electron until reacted upon. Now, I know, right? Dun dun dun. Cover up the green fluorine. How many electrons does that fluorine have? 8. Cover up the red one. How many does that one have? 8. Is that an octet? Yeah. Exactly. So now you represent that by doing this. There you go. Now, that line is a single bond, represents how many electrons? 2. Cover up the green hydrogen. How many electrons are on the fluorine? 2, 4, 6, and the line counts for 2. So there's 8, right? Cover up the red one. How many are on the red one? 8. The line counts for 2, 4, 6, 8. So that fluorine has, both fluorine atoms have a complete octet. So that's stabilizing. Okay, that makes it more stable, right? So fluorine actually will exist as F2. And well, I don't need to do that. If you wanted to buy commercial fluorine, if you want to buy F2, you would buy, if you want to buy fluorine, sorry, you would buy it as F2. You cannot buy F. It's impossible. You have to buy F2. Now, I hope, I don't know this for sure, but I certainly hope if you call up a gas company and say, I want some fluoride, I certainly hope they ask you lots of questions. Because even though this is stabilized, it is certainly not stable. It will react very quickly. In fact, if you want to come back with me a little bit of history of my life, thinking back to the days when I almost died. I wasn't in the room though, thank God. A friend of mine was working with fluorine gas. Part of his research was fluorine research. So anyway, fluorine gas tanks, you can buy them. It's very commercially available from supply houses. Fluorine comes with a certain kind of regulator. Like you have a big old tank under pressure, and you put what's called a regulator. You screw it on there, and it steps the pressure down from 2,000 pounds to like 3 pounds, so you can just kind of trickle it out really slowly. It's a certain kind of regulator. It only fits a fluorine tank. And when you work with it, you wear gloves. And you wear goggles and a face mask too, because the stuff's explosive, or it's very, very dangerous. Anyway, so he put some what's called Teflon tape around the regulator's threads to make sure it's a good seal. But he did it without gloves on. He put the Teflon tape around the fluorine without gloves on, which is a no-no. You're not supposed to do that. And anyway, so he tightened the regulator up there, cranked on the cylinder. The fluorine gas hit the regulator, hit the oil on the Teflon tape. Now the oil came from his hands. You know how much little bit of oil is on your hands. It's not much, right? But enough to detonate the fluorine. The fluorine went poof, and the regulator went boom across the room, and the fume hood caught on fire. Because fluorine will react with damn near anything. Because it's so unstable, it loves to react, especially with hydrocarbon, which is carbon-hydrogen bonds. What are you made of? Carbon and hydrogen. Very, very dangerous situation. Yeah, he didn't die, but boy, he was scared.
Is it split when it starts to burn? Is that what makes it burn?
It's probably that and the heat from the reaction makes everything burn. Yeah, so it gets really, really hot. It's fun, man. Chemistry's cool. All right, double and triple bonds. Let's talk about those real quick. Let's draw a double bond. Let's talk about another molecule that's very near and dear to all of our hearts. Oxygen. Oxygen. How many electrons does oxygen have in its valence shell? 6. Very good. 1, 2, 3, 4, 5, and 6. Let's draw another oxygen. 1, 2, 3, 4, 5, and 6. Oxygen requires 2 more electrons to fulfill its octet. Requires 2 more. So they kind of happen by each other and say, hey, look at those. I don't mind if I take my electron from you. And then they become this. Oxygen, electron, 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 electron. And then the black one electron, 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 electron. Okay, so now let's cover up the green one. How many electrons does that green one have? Or the black one have, excuse me? 7. How many does the green one have? Uh-oh, that's not good, right? They got to have 8. Got to have 8. So this oxygen and that oxygen look at each other and say, hey, you have another electron, I want it. And they try to steal the second one. They couldn't get the first one, you may as well get the second one. So then what happens? Something even more interesting. Well, I think it's more interesting. There you go. Electron, 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 green one, and then the green guy. There you go. All right, now cover up the green atom. How many electrons does this oxygen have? 2, 4, 6, 8. See that? Cover up the black one. That one has 2, 4, 6, 8. See how that works? Ah, see right here. How many is right here? 4. Cover up the black one. There's 4, 6, 8. Okay? So now they're not just sharing 1 electron each, they're sharing 2 each. Now that looks funny. That just looks weird. That's hard to look at. So what do? Very easy. Just do this. Green oxygen and the black one. And the black one. And now, instead of 1 line between them, we'll draw 2. That's a double bond. A double bond. Now, every line counts for 2 electrons. Is that correct? A double bond has 2 lines. So how many electrons are there? 4. Exactly. So cover up the green oxygen. How many does the black one have? 8. 2, 4, 6, 8. Cover up the black one. How many does the green one have? 8. 2, 4, 6, 8. Simple, right? Have you ever wondered why oxygen, when they talk about it in biology, is O2? Ever wondered that? That's why. Oxygen must exist as O2 in the pure form because it has to have an octet. Neat, huh? And you thought chemistry didn't apply to biology. It does. Which is why all the biologists say take chemistry. Okay. Is that okay? So that's oxygen. If you buy oxygen from the store, from a supply house, or you breathe it in from the air, that's oxygen. O2, it has a double bond. Neat, huh? Chemistry's fun, right? Exactly, see? All right, so that's pretty easy, right? You guys got that? Single bond counts for 2, double bond counts for 4 electrons. Okay? Okay, everybody got it? Let's move along to the triple bond. Nitrogen is the best example of a triple bond. Nitrogen has how many valence electrons? 5, there you go. 5 valence. Okay. Nitrogen needs 3 more electrons. It has to have 3 more electrons to satisfy its octet. So let's just see here. Well, we all know that these 2 will try to steal, and those 2. But now we have this one and that one. Right? See the 2 with the arrows pointing at them? They will also try to steal from each other. So without prolonging this, I think you guys got the hang of this now. What you'll get, and this is going to look kind of funny, there we go. Looks kind of funny, I know, but stay with me. So if I cover up the green nitrogen, I have 2, 4, 6, 8 electrons around the red nitrogen, don't I? Right? Cover up the green one. 2, 4, 6, 8. Right? Everybody? Now, That looks really strange. That looks really hard to deal with, so let's make it simple. There's nitrogen. 3 lines towards the green nitrogen. There you go. Now, every line counts for how many electrons?
2.
How many lines are there here?
3.
3 times 2 is?
6.
Exactly. How many electrons are around the red nitrogen? 8. How many are on the green one?
8.
That's simple. Nitrogen. Have you ever wondered why nitrogen is N2? That's why. Purified nitrogen has to have an octet like all the other atoms. So purified nitrogen is N2. Now that doesn't mean it can't be found in other ways. You can get NH3 and all kinds of other ways. But that's purified nitrogen. It comes as N2. If you buy pure nitrogen from the supply company, it's going to come to you as N2. Pretty neat, huh? Not hard though, is it? Not hard. Okay, so that's pretty easy. Let's do something that's not really any harder, just a little bit more involved. CO2, carbon dioxide. We've all heard that. Let's just draw its structure. How many valence electrons does carbon have? 4. 1, 2, 3, 4. How many valence electrons does oxygen have? 6. 1, 2, 3, 4, 5, 6. And there's 2 of them, yeah? Formula says there's 2 of them. So let's draw the other one over here. Okay. So there's carbon. Carbon needs 4 electrons to make its octet. Each oxygen needs 2. That's convenient, right? This oxygen needs 2. That oxygen needs 2. This carbon has 4 spots. Right? That's pretty convenient. Pretty convenient. So let's see now. These electrons can, start to try to steal each other. Those electrons can try to steal each other. These ones up here, and those ones right there. Okay? So far, so good. So those electrons that I circled in the blue square, they're just trying to, rip each other away from their owner atom. So that will become this. Oops, missing something here. No, 2, 4. Yes, missing. No, that's good. That's good. That's good. And carbon is black. Carbon, black. There we go. Black over here. And the red one. Okay. 2, 4. That's why that looks so funny. I wonder why. There we go. Okay. So now, this looks odd, right? You got a whole bunch of dots everywhere. So what does that become? Just like before, carbon will be double bonded to the red oxygen and to the green oxygen.
Is there a reason why you're not putting them north, south, east, west?
Yeah, just to make the structure look prettier. Oh, which ones? You mean these ones?
Yeah.
Yeah, there's a reason, but you don't have to worry about it. It has to do with electrons are more stable in pairs than by themselves. That's a general chemistry topic. You don't got to worry about it.
So if you were writing north, south, east, west, will be wrong.
Oh, I would never ask you to do that.
Okay.
This molecule is too hard for an exam. You'll get easier ones than this, but not anything like this. At this level, asking you to draw that would be really, really, really rude. Okay, let's cover up that oxygen right there and that one right there. How many lines does carbon have drawn to it?
4.
4 times 2 per line is 8 electrons. So carbon has an octet, right? How about that oxygen right there, the green one?
8.
Is that an octet? How about the red one over there? 8. So everybody here has an octet. So carbon dioxide is stabilized. Okay? It does react, but it's just stabilized. Okay? Make sense?
The carbon dioxide, right?
Yep, that's carbon dioxide. That's what it looks like. It's straight. Like it's 1, 2, 3 in a straight line. Kind of cool. Kind of neat. Okay? Everybody at least somewhat content with that. Now, it's really, again, that's a challenging one for this class. So don't freak out about it too much. Just understand that nonmetals will bond to nonmetals to make octets. All right. And we just did that one. I did all this stuff. Okay. You can write this down if you want. It's a table in your book. This is when you use prefixes to name compounds. Now, remember I told you when you look at ionic compounds, it's not barium dichloride. It's just barium chloride, BaCl2. You don't use di, tri, tetra, penta in ionics. You use them in covalence. Yeah?
I have a quick question about the CO2. Do you have to put like when you form it up, you have to put the oxygen, carbon, and the oxygen again?
Yep. Mm-hmm. If you draw it any other way.
That way?
What's that?
You have to know how to set it up that way.
Yeah, I would like for you to know why it's set up that way. If you draw it any other way, you'll put more than 8 electrons on oxygen, which is why it has to be that way. And in general, when you're drawing these kind of structures, almost always, I'm going to say almost because it's not always true, almost always carbon's in the center. Almost always. So if you're ever in a situation where you have to draw a structure and there's a carbon, just guess that it's in the center. You might be wrong, but you're probably going to be right. All right. So in ionic, I told you we don't ever say barium dichloride or magnesium dibromide. You just say magnesium bromide, right? In ionic, this is where the dis and the tris and the tetras come out. Why? Because you could have carbon dioxide, right? Everyone knows that one, right? But you can also have carbon monoxide, right? They both exist and they're both relatively stable. Okay? So that's why we have to use the monos, dis, and tris, because there's more than one way, there's more than one formula for a name. So for example, if you just said carbon oxide, well, is it carbon monoxide, carbon dioxide, carbon trioxide, carbonates, bicarbonates? There's all kinds of carbon oxides. See what I'm saying? So you have to be specific. This one, you all know that one, is carbon dioxide. Right? Everyone knew that one. Carbon dioxide. This one, that's carbon monoxide. Okay? So that's why we have to start pulling out the prefixes to let the user or the reader know how many atoms there are. Okay? Because if I had just said carbon oxide, you would have been like, that doesn't make sense. Is it carbon dioxide, carbon monoxide, carbon, tetraoxide, or anything else like that? Okay? Is that okay with everyone? Yes. So that's why we have to use it. So let's look at this one. NCl3. Now, on an exam, the first thing you're going to want to do, if you don't already know, is say, okay, nitrogen and chlorine. Run to the periodic table and say, okay, nitrogen is a nonmetal. Chlorine is a nonmetal. Okay. They're both nonmetals, so I have to use the covalent rules. I cannot use the ionic rules. So that's the first thing. It's covalent. Okay, so it's covalent, so now I know it's N, 1 nitrogen, 3 chlorine. So it's nitrogen trichloride. Okay? You don't say mononitrogen. The mono is assumed. Okay? So it's nitrogen trichloride. The mono is assumed. Make sense? Is that okay? I think everyone agrees that's easier than ionic. Right? Maybe? Hope so. Now that you've seen your first example, let me give you a little study tip. What was that?
Repeat that, nitrogen tri.
Chloride. What was that? Oh, yeah, of course. Here's a little study tip. You all know sodium chloride, right? Everyone in this room knows what sodium chloride is, right? NaCl. So here's a study tip. Na is a metal, Cl is a nonmetal, right? You all know NaCl is a salt, or ionic, right? Everybody knows that, yes? NaCl, metal to a nonmetal, ionic, use the ionic naming rules, sodium chloride, okay? You all know carbon dioxide, CO2, right? That's covalent. Use the covalent rules. Carbon, 2 oxygens, carbon dioxide, okay? That's how I remember it. Make sense? Yeah, everybody? Or find your own way. But that's how I remember it. Okay? So everyone's looking at me like I'm some kind of crazy man, but okay, use your own way then. That's fine. Let's try some different examples. A, SiCl4. Before you even try to guess, run to the periodic table. And you're going to see that silicon is not a nonmetal. Uh-oh. Now what do?
We have to use the ionic rule.
Careful now. Silicon's also not a metal. It's a nonmetal. Or sorry, it's a metalloid. Right? A metalloid is not a metal, is it? No. So you treat it like it's a nonmetal. First one was a trick question. Gotcha. Okay? But I gave you the trick questions in class, so on the exams you'll be like, out of the park, home run, no problem. So a metalloid, even though it's not a nonmetal, it's not a metal either. So you name it as a covalent. Okay? So the first one, SiCl4. Si is? Silicon. Chlorine, so you name it as chloride. Silicon, 4 means tetra. Silicon, tetra, chloride. That's the hardest one, the 4, the tetra. That's just kind of weird. People want to say quat, but it's not quat, it's tetra. Okay? Silicon, tetra, chloride. Tetra means 4. So far, so good? Everyone kind of like that, sort of? The next one, P2O5. Now we have more than one atom at the front. So we have to tell people that. We can't say phosphorus. We have to say diphosphorus. Does that make sense? Because there's more than one, we say di. All right? Phosphorus, jeez. Diphosphorus pentoxide. Does that make sense? Pent is 5, pentagon, 5. And the last one. Now we have 2 chlorines. So what will we say? Dichlorine. 7 is hepta. So it'll be hept oxide. Make sense, guys? Is it a little bit clear? The hardest part here is knowing that the 7 is hept. Okay? That's pretty straightforward though, right? Everybody like that? Dichlorine, hept oxide. Let's do some more examples. What if I put down NO2, N2O2, N2O3. I'm just making these up. I have no idea if they exist. NCl3. How about those 4? What's the first one? The top one. Nitrogen dioxide. Very good. What would that one be? Dinitrogen dioxide. I have no idea if that exists, by the way. But that's how you name it. How about that one? Very nice. And the last one? Very good. Three. And I don't know. I just totally made that last one up. What's the first one? The first right. Diphosphorus pentoxide. This one? I don't think that one exists. That one? That one's totally made up. Heptaphosphorus trioxide. Oh yeah, chloride, sorry. It's not an O, it's a Cl. 7 is hepta. Hepta. Okay? That's a weird one, hepta.
So we always drop the A at like penta.
Yep. Whenever there's 2 vowels together, drop the A.
You repeat the last one?
Be heptaphosphorus trichloride.
Let me, do we have to memorize the mono?
Yeah. There's only two that are weird. There's hepta, that's weird, and tetra, that's weird. 4 and 7. The other one's kind of di, tri, penta, hexa. They all kind of make sense. Octa. Just those two that are kind of weird because you don't normally see heptagrams or tetragrams. Well, tetragram's a square, I guess. Try those ones. There's 4 more for you. These ones all exist, by the way. These ones are kind of made up. Did y'all get them? Everybody? All right, what's the first one? Carbon monoxide. Carbon monoxide, very nice. B.
Nitrogen dioxide.
Dioxide. C.
Phosphorus trifluoride.
And D.
Tetrachloride.
Carbon tetrachloride. All right, very good. Everyone kind of has it now, right? Let's find out. Where is it? Where is it? I don't want to do that one. There it is. Do that one. That's a mixture of ionics and covalents. And we have another little nuance in here too, what I'll show you in a second. Here are your polyatomics. NH4 is positive 1. It's called ammonium. CO3 is carbonate. And I'll just tell you the elements. You may not know them. Cu is copper. Ba is barium. What else we got up there that might be weird? So, you know, sulfur, oxygen, you know all those ones. Nitrogen. All right, give that a try. That's a pretty hard learning check right there. Oh, PO3. That's another one, PO3. Phosphite. Oh, must be -3. tougher, huh? Because now they're mixed together, which is how you'll see them on the exam. Don't forget, for your exam in a couple weeks, make sure you read the textbook. Multiple choice questions come primarily from the textbook. All right, let's talk about this. We're running out of time. That's why I got to move this along. I'm sorry to be abrupt. Now, well, first of all, when we look at questions like this, the easiest thing to do, I think, is to first of all identify which one's ionic or covalent. And that's what the question asks you to do. So which one of these, well, let's just go through them. Is A ionic or covalent?
Covalent.
A is covalent. There's no charges, there's no metals, so it's covalent. B, ionic. C, oh, careful now. That's the trickiest one you're ever going to see in this class.
It's a transition.
Look at the NH4 and look at the PO3. Right? Everybody with me? This is the hardest one, so you're going to want to pay attention to this one. NH4 is right here. It's ammonium, right? Remember I told you guys that there's only one exception to the metal rule? Remember I told you I was going to bring it up eventually? Well, eventually came. This is NH4. What's the charge in NH4? Plus 1. PO3. PO3 is right here. What's the charge on PO3? -3. What's an ionic bond made of? Just in general, what's an ionic bond made of? Or that's that works 99.9% of the time, but there's a positive cation with a negative ion, right? That's an ionic bond. Usually it's a metal and a non-metal, and 99.9% of the time, that's what you got. I told you there'd be that 0.1% of the time, and the exception, that's it. Ammonium. Whenever you see NH4, your mind must immediately go to ionic. NH4, ionic. Okay? Everybody, do this. NH4, ionic. Do the little thing with your head too. Ionic. Just go right to ionic. Because NH4, if it's in a molecule, it's ionic. Guaranteed. Okay? Very good. That's a trick question. But now that you've seen it, you're like, oh, okay. Ionic. And you remember that. I'll see you guys in the exam doing this. It'll be really cool. D. Is that ionic or covalent? That's definitely ionic because there's a metal there. The last one. It's covalent. 2 nonmetals. Right? All right, let's name the first one. Sulfur. Trioxide. B. Everybody. Barium chloride. It's not barium 2 because barium is a group 2 metal. Right? So you don't need the Roman numeral. This one is ammonium. There you go. There. See, now that you've seen that little trick, you're going to be like, oh, ammonium, ionic, no problem. Not even hard anymore. This one, now we got to be careful. Copper is a transition metal, isn't it? So what's the charge in the copper? It's copper 1. We'll go over that one here in a second. It's copper 1 carbonate. Hold on, we'll go over it in a second. Let me finish number E, or letter E, and we'll go back and we'll do this one. We'll put a little star beside it. We'll go back and do it. All right, N2O4. What's the name? Dinitrogen.
Trioxide.
And it's 4, so it's tetra. Tetroxide. Tetroxide. I took the A out because when the A and the O come together, just drop the A. Okay, let's do letter D together, and then we'll call it a week. Okay, so now, why is it copper 1? So we got Cu, 2, CO3. CO3 is carbonate. So the carbonate has a -2 charge. minus 2 total charge. There are 2 coppers that are coming to our party. And they must be a total of positive 2, right? So each copper is plus 1. Because plus 1 and plus 1 is plus 2, yes? The charge on the metal is plus 1, right? So it's copper 1. Copper 1 carbonate. This is where the number 1 comes from. Okay? It has nothing to do with this. This has nothing to do with that. Okay?
So why number 2 is not diamond?
Because barium is a group 2 metal. Group 2 and group 1 metals do not require Roman numerals because they can only be plus 1 or plus 2. Barium cannot be anything more or less than positive 2. Well, it can be neutral, sorry. But it can't be positive 1, it can't be positive 3, it can only ever be positive 2. All right? No class next week because I will be at a professional development seminar. So will the whole campus, so don't just think it's me. And when I come back, we'll have an exam. This will be on it. Everything through today.